Here we're going to continue our discussion of non-ideal conditions. We talked a little bit about non-ideal conditions when we had gases that were not ideal. We introduced the term fugacity and fugacity coefficient. Let's just continue along there. Let's define a quantity called activity, and we'll give it the symbol A. The activity will be, for gases, exactly what we said before. So instead of, say, pressure over some pressure of some component divided by, well, here, why am I drawing on this? Let's draw over here. So we're just reviewing what we said in the last lecture. We introduced a fugacity to be equal to the fugacity coefficient times pressure, so that when we put into equations that we initially derived from using the ideal gas law, now pressure over pressure, some standard state for some component I, let's make this some component I, that now goes as fugacity some component over pressure, standard state pressure. We're going to define this quantity as activity of that particular species I. So activity, note, is a ratio of two things that have the same unit. So this is unitless. If you have ideal solutions, or ideal, in this case, ideal gases, the activity will just be equal to the ratio of pressures. But if you have non-ideal gases, the activity will be ratio of fugacity divided by the standard state pressure. So that's what we mean. We're just introducing a new symbol, the symbol A, and we're going to call that activity. Now for solutions, this is something new here. The activity is going to be defined as a mole fraction. That is a fundamental unit of concentration when you're talking about in physical chemistry, when you talk physical chemistry, mole fraction. So the activity of something in solution will be equal to the mole fraction of that component in the solution. And then just like we introduced a fudge factor fugacity coefficient here we're going to introduce an activity coefficient, gamma, Greek letter gamma sub I. So now for solutions, this was for gases up here. For solution, the activity of I is going to be defined as the mole fraction of I in for ideal, or will be defined as a activity coefficient for that species times the mole fraction I. This is a non-ideal. So the activity coefficient is equal to 1 for an ideal component. So that's what we're doing there. And now here for pure condensed phases, we'll get to this part in just a minute. For pure condensed phases, the activity is equal to 1. The activity of a pure phase, or pure substance, is equal to 1. What does that mean? Well, just let's see what we do here. The chemical potential of that substance will be equal to the standard state chemical potential plus RT times the natural log of the activity. If this is equal to 1, then this is equal to, and that, the logarithm of 1 is equal to 0. That is equal to 0. So that mu is just equal to mu 0. So if the activity is 1, which we say it is for a pure substance, then the chemical potential will be the chemical potential of the standard state, which will be the pure substance. So it sort of makes sense to define the activity equal to 1 for a pure substance. Oftentimes, we don't measure concentration in terms of mole fraction. Instead, we use molality. So what is molality? Well, recall from introductory chemistry, the molality, which is given the lower case letter m, that is defined as the mole of solute per kilogram of solvent. Mole fraction and molality are similar. Let's just show that. Let's look at mole fraction. Let's look at two-component system. Mole fraction will be the number of moles of say, the solute divided by the number of moles of solute plus the number of moles of solvent. So 1 corresponds to solute, N2 corresponds to solvent. And we have a two-component system. And you distinguish solute from solvent by concentration. In a two-component system, the one that has the lower concentration is usually called the solute, and the one the higher concentration, the solvent. Now let's make the assumption of I have a dilute solution. This ratio then becomes just N1 over N2. So dilute solution, which implies that N1, the number of moles of solvent or solute in solution, is much less than the number of moles of the solvent. So, okay, we're starting to make approximations already. And also, remember let's contrast this with molality. Molality is the number of moles of solute divided by mass. So this is mole fraction of 1. This molality of 1 be the number of moles divided by the mass. Number of moles, that's the same. So all you need is a conversion to go from mole fraction to molality. Conversion, how to convert moles to mass, and that is the molar mass. So if we multiply both sides of this, so this is right down here again, so it's the mole fraction of solute, that's equal to N1 over N2, multiplied by M, the molar mass of the, put a 1, molar mass of solvent, sorry. So that should be a 2 because we're using 2 to denote solvent. 2 there, and multiply, we can do that, multiply by 1. This then, moles times the mass per mole, this is the mass of the solute. Let's go ahead and plug those numbers in. So the chemical potential of the solute is equal to the chemical potential of the solute in the standard state plus RT times the natural log, let's say it's ideal, get rid of the activity, well, all right, we'll put it in, times N1 over N2 times the molar mass of the solvent. And what did we do here? We did dilute solution, and that's the activity coefficient of the solute. So that's mu10 plus, let's pull out an RT times natural log of M2. Remember, the log of products is the sum of the log of the individual things, so we can pull out an M2 and add that as an additive term, plus natural log of gamma 1 times N1 over N2 M2. And what we have here we'll define as a new standard state prime. And this then would be the molality, lowercase m. If I make that lowercase m, molality of solute. So just generally that's how you convert from mole fraction to molality. The big assumption is you have a dilute solution. And then any constants you have, you incorporate that into a new standard state. The new standard state then would be molality rather than pure substance, for example. Okay, so that's where that comes into play.